So what that means is later today, I'll put the answers for the review on Blackboard. And then tomorrow we'll mostly do nothing new. Today we'll get into double integrals, so I might do one double integral at the beginning just to keep you in practice, because then we won't see it again until next Tuesday, because Monday is Memorial Day. So just to keep you in practice a little bit, but it won't be on the actual test. And I guess that's it. So start the usual thing, which is we start with homework. We're in 2.10. So I start with an easy one. As usual. So being lazy as usual, not writing the whole thing out. Sometime later today. So I've written up about half of them. So it'll probably take me another hour or something like that to finish it after class, and maybe 4 or 5. Oh, also I did have one other thing, which is I did get an email from the TA Anupam, and he said he was running behind. So the quizzes won't be fully graded until tonight. Sorry about that. And but the ones that I graded them over the weekend, but I'll wait to put the scores up until they're all there. But again, if you send it to me, not through Blackboard, I can email you your answers if you send me an email. So this is the shorthand for, we want to find the absolute minimum and the absolute maximum for this function, really simple, on this region. And so we do the usual step now. We've done this now for the last few classes, is we, actually this part from even longer, we get the gradient, we set them both equal. As I said, this is a simple one, so we set them both equal to 0, and obviously we just get the 0.00. We check, make sure it's in the region. It is, which means that is a possible answer, because we know that the absolute minimum and absolute maximum will either occur at critical points or on the boundary. So now we have to look at the boundary. And the boundary is x squared plus y squared is equal to 4. So I can solve for one of them. Doesn't really matter which one. Because it's not a function, I get two possibilities. The square root of 4 minus x squared, or the negative square root of 4 minus x squared. Notice in doing that, I'm creating endpoints. Obviously, a circle doesn't have endpoints, but now that I've solved for y, what are the endpoints that we get? Because now we're looking at just the top half of the circle, which does have endpoints, and those endpoints are at plus or minus 2, 0, right? Minus 2, 0, and 2, 0. If we had solved for x, then we would have gotten the endpoints 0 and plus or minus 2. So which endpoints we get will depend on which way we solve it. So critical point and endpoints. And now we plug in, and we get f is equal to the x times the square root of 4 minus x squared, plus or minus, but it should be obvious that that's not going to come into it, because we're going to take the derivative set it equal to 0. The sign outside is not going to matter. So we take the derivative, and it is product rule. So take the derivative of x, leave the square root alone, leave the x alone. The square root of 4 minus x squared is going to be so it's x to the 1/2, so 1/2 x to the negative 1/2. So we're going to get a square root in the denominator. And then times the derivative of the inside, which is negative 2x. So we have a 1/2 from the exponent and a negative 2x. So we're going to get a negative x here. I'm trying to make it so it all fit on the one page, which is why I'm condensing it. But I get something like that. And then to solve, I can do one of a couple things. What I'm going to do is get a common denominator. So that means the first term I have to multiply by the square root again. So I'm going to get 4 minus x squared, and then minus the x squared. It's going to give me, it is, but remember when we're taking the square root of this, which is the 4 minus x squared to the 1/2, we're going to get the 1/2 brought down from that. So the negative x is 1/2 times negative 2x. So the only way this can be 0, obviously the denominator can't make it 0. So the only thing we have to worry about a little bit is if our answer ended up involving x equals 2, there'd be a problem, because obviously it's not defined at 2. But it's not. So we set the numerator equal to 0, which gives us 2x squared is equal to 4, and therefore x is equal to plus or minus square root of 2. And that gives us lots of possibilities, because once we get that, that gives us y is equal to plus or minus the square root of 2 if I plug it back into our function. And so we get our list of possibles. That almost says possible. Is the 0, 0, the negative 2, 0, the 2, 0, 0, and all of these. So negative square root of 2, negative square root of 2, negative square root of 2, positive square root of 2, positive square root of 2, negative square root of 2, positive square root of 2, square root of 2. So I have all the possibilities, critical points and endpoints, and then any critical values on the boundary, of which we have 4 in this case. And then what do? Since it's obviously I'm going to put on to the next page. Right, so plug it into the original function. So those don't come up because of the way we solve it. Here we solve for y. Here's the circle, which doesn't really have any endpoints, but since we solved and got y in terms of the upper half and the lower half, we've broken it up into the upper and the lower half, and therefore we get the 2 endpoints are there. Notice there isn't an endpoint at 0, 2, and when we solved, we didn't get that. On the other hand, if we had solved in terms of x and instead of y, so we got x equals plus or minus the square root of 4 minus y squared, then we would have broken it up this way. And then our other endpoints would have been 0, 2, and 0, -2. So it's kind of weird that we get different possibilities depending on which way we do it, but it works out the same. No, just one of them. So any other questions on this? This is the main part, because then the other is just you plug them all in, whichever's biggest is the maximum, whichever's smallest is the minimum. But so any other questions on this? Okay, so let me actually do it though. No, in that case, so in terms of the critical points, which I'll write in a second, it's actually let me write them and make sure that that's what you're looking at. So we got that y is equal to plus or minus the square root of the 4 minus x squared. And when we solve, we got x is equal to plus or minus square root of 2. So when we plug in, we get the square root of 2, but then the plus or minus. If we'd solved the other way, we would have gotten x is equal to 4 minus y squared. When we plug that in, we would have gotten y is plus or minus square root of 2. And again, when we plug in, so we would have still gotten these 4 points no matter which way we solved. Oh, so there is no, so 2, 0 is correct. This is just me being silly. That's what I meant. Sorry about that. And these are all 0. These are all 2. And these are both -2. And so therefore, there's a global maximum of 2 points. And global minimum at 2 points also. Okay, so there's the final answer. Any questions on this? So there's kind of the full step again, which is first we found critical points. For which part? All 4 points in x and y axis for boundary points? Do you mean, so we chose 2, 0, and -2, 0? But we could also choose 0, 2, and 0, -2. Is that what you mean? Okay. So, as I said, here's what we did was we had the circle, but the way we looked at it once we solved, right, we looked at the top half of the circle. There it is. I think it's pretty obvious that there are 2 endpoints. And then we looked at the bottom half of the circle. It's almost a circle. which have the same endpoints, so I don't get anything new. If we looked at it by breaking it into the left half and the right half, we'd instead get the, so if I start drawing it this way, so I looked at the right half, then I get two different endpoints. You can see in this case it's not going to matter because I'm doing x times y. In each case I get 0. So neither one's getting me the point I need. And that's always going to be true. So there are cases like this where you can set it up in two different ways and see endpoints in two different ways, but it's not going to matter for the final answer. So any other questions on this? Okay, so let me do another one. Jump to 19. And this one I'm doing just so we do it one or two that aren't boxes. So this is going to be a word problem. And I'm going to do this one, and for the next section I'm going to do another one that's also not a box. But on the actual test it's probably going to be a box, or one like not this one, because this is going to be a bit more elaborate, but the one that we do next. Or the one after, I forget which one we do it at. So this one says, suppose we have a ridge. And it's modeled by the graph y equals 64 minus x squared. And then we have a plane that's going to fly over the ridge, which has a flight path modeled by this. And what they want to do is they want to put a light at the point on the ridge that's going to be the closest to where the plane is. So over here is, I'll exaggerate, there's the ridge, the y equals 64 minus x squared. And we have the, oops, oh, doesn't matter. And then we have the flight path. So what I'm going to do is find the point on this flight path that is as close as you can get. And obviously that point is not it. As close as the flight path is going to get to that ridge. So first, they present it as these are both y in terms of x. But the x's don't have to be the same. So let me put them as points. Oh, sorry, Jane, I missed your question from before, which is, right, so I draw since I broke it up that way, I drew the graph for just the top part and then separately just for the bottom part. And when you do that, then that's when you get the endpoints. So we get these 2 points because, as I said, they don't have to be at the same value of x. And now I want to minimize the distance. And I'm going to change that in a second. Oh, so just I put in a into this. So if I put a into this, I get 64 minus a squared, which is y. If I put b into this, I get 100 minus b over 2, which is again the y. So I put a and b into the two functions that are given. So I want to minimize the distance. I'm not going to write it because I'm going to change this a little bit in a second. What is the formula for the distance between 2 points? This is kind of a pain to write. So I just say it's the square root of the sum of the squares. So it would be the square root of the x2 minus the x1 squared. Oh, there we go. Square root of x squared plus y squared. Yeah, that's a shorter way of doing it. Notice, if it's going to be a minimum for the square root of that, it's also going to be the minimum for the function itself. So what I'm going to do is, instead of minimize it to make it a slightly simpler problem with the same answer, I'm going to say let's minimize the distance squared. That we don't have to worry about the square roots. And it should be pretty obvious that if it's a minimum for the distance, it's going to be the minimum for the distance squared, because we can't have negative distances. So let me call that f, distance squared, and then it's the change in the x. And then the change in the y is squared. So as with the other other word problem that we did, you have a bit more to do to set up the problem, but once you do, it becomes a little bit easier because there's going to be just one answer. Because it's pretty obvious that as the plane is moving, it's getting closer and closer until I get to the closest point, and then it gets further and further away. So there is no maximum, so there's not going to be a critical point for that, and there's just going to be the one minimum. So when we get the critical points, there's only going to be one, and that's going to be our answer. So take the derivative. I say with respect to x, but let's make that an a because that's what I'm using. So I could multiply it out, but you'll see when I take the derivative, it'll be a little bit nicer if I don't. The only little thing is, of course, the 100 minus the 64 is 36, so I will simplify that part. So the derivative with respect to a is going to be the negative 2 the b minus a, or 2b minus a to the 1 times the derivative of negative a, which is negative 1. And then plus, this time I'm not sure why I'm doing it this way, not the other one, 2 times the whole thing on the side, which is something that's simplified, the 100 minus 64. So I'm going to get that. If I take the derivative with respect to b, I get, it really doesn't like my writing. And so then both equal to 0. Just so I want to do at least one that's a bit more elaborate. You wouldn't see anything like this elaborate on a test. So looking at this, what I would probably try to do is to simplify things by addition and so on. So I notice that each term has this in it. So what I'm going to do is multiply this first by nothing. That's 4a. And this is -1 times the same thing. So if I multiply this by 4a and add 2, then this second term is going to cancel. Because I have 4a times that what's in the parentheses minus 4a times what's in the parentheses. And then I have the 2 times the 4a, and then minus the 2. So as I said, this is more elaborate than what you can see, but you can see that it is something that isn't too terrible once you see the little trick. And so you can see there are two possible answers. One is a is equal to 1/4, which should be obvious since we know that there's only going to be one answer. That's going to be the answer. But the other possibility is a is equal to b. And if I plug that into the, doesn't really matter, the second equation, I guess. So if I plug this into this equation, the first term is just going to go away. I don't care about the constant, even though it's -1. So I get 36 minus b over 2, so 36 minus a over 2 plus a squared. And if you look at that, I don't really have much room for it, but does that have any solutions? So that's 36 minus a over 2 plus a squared. No, because if you look at the root, it's going to be the square root of b squared minus 4ac. Since a and c here are both positive and b is just 1/2, it's going to be negative. So it only have imaginary roots, so this is not it. So therefore this is the answer, which means the point is 1/4, and then plug it back into this, the 64 minus 1/16. So as I said, unlike the last one, it's harder to set up, but once we have it set up, it's a little bit, in general, a little bit easier because we don't have as many points to try. There are, again, boundaries, but again, the boundaries are pretty obviously not the solutions, because pretty obviously somewhere around here it hits the ground, which is where it takes off, and that's pretty obviously not the closest point. And if I keep going, the other boundary is off to infinity, and that pretty obviously is not the closest point either. So the boundaries in this case are pretty obviously not the answer, and so the one possibility we get has to be the answer. So in a second I'll do it another one like this, but simpler. So any questions on the idea? As I said, I want to do at least one more complicated one, even though you're not going to see one like this on the test. So those are the couple I want to look at in 2.10. As with 2.9, there really aren't that many. Any others from 2.10? Up to 7 or 9 before I finish my question. Give me a second. Oh, so 9, if you remember, I said that 9 and 10 don't worry about. Those both use the parameterization stuff, which is in 2.8, which we skip. So let's look at 7. Yeah, it should be okay too. So 7 says, here's our function, and it's the curved triangle where x goes from 0 to 4, and y goes from 1 to e to the x. So here's y equals 1. Here's y equals e to the x. And then they say go from x equals 0, which is just there, x equals 4. So here's our little, they're calling it a curved triangle. And so, same as the last one, they want to find global minimum or maximum. So simpler than the last one. More similar to 2. So we take the derivatives. Okay. Set them both equal to 0. And this is kind of boring. So let me use the top one. So what does the top one give us? What are the possible values that make that 0? And then you'll tell me why we don't really. Actually, no. So either y equals 1 or x equals 0. Yep. So if I then put that into the other derivative, so I put in x equals 0, what does that give me? 4 equals 0, so nothing. So give me something that obviously doesn't have a solution. If I put in y equals 1, I get x squared plus 4 equals 0. And does it have a solution? Nope. So no critical points. So kind of a boring one here. And now we want to put in the endpoints. So first, let's just read off what are corners. So this is 0, 1. This is 4, 1. And the last one is somewhat. So let me actually, in a second, write down what they actually gave me. And then the other is 4 to 4. So what they actually gave me is they said x goes from 0 to 4. So 0 is less than or equal to x and 4. And 1 is less than y is less than or equal to e to the x. So this is what was actually given. And so I graphed y equals 1. I graphed y equals x. I graphed x equals 4, and then I noticed that, well, at x equals 0, we just have the point. So this is what was given. And I often do, I was being lazy to try to save some space. So we didn't get any critical points, but we do have the corners, so there are possibilities. And now what do we do? Right, so plug in the boundaries. So there's that first part. This is no critical points and corners. So I can put in y equals 1. And remember, for this, we're plugging now back into the original function. So that's going to give us f is equal to x squared plus 4. Well, not e to the x by itself. So I plug that in. I take the derivative. So I get the critical points for this boundary, which gives us x equals 0. And it gives us the point that we already have. Oh, thank you. Oops. Right, so nothing there. And then x equals 4. Let's see if I can do this one right. X equals 4 gives 16 ln of y plus 4y. Derivative of that is 16 over y plus 4. Set that equal to 0. And that gives y is equal to -4. And do we care about that? No, because it's not in our, so we have the point 4 comma -4. We don't care about it because it's not in our region. Being a fairly boring problem so far. And finally, we have the boundary y equals e to the x. No, so it can't be. So the idea is that 4 can't be 0, which means there are no critical points. So we don't get anything except for the boundaries, which we already had. Derivative of f is 4. 4 can't be 0, which means there are no critical points. Oh, so right. So derivative. Sorry. So the derivative is 0, but 4, whichever way you want to think of it. So the derivative of 4 is 0, which is 0, but the function is just 4, which obviously doesn't have any critical points. So putting in y equals 1 gets a little weird because we're getting a constant function. And so you have to say, oh, it's a constant function. There can't be any critical points. So sorry about that. I said that wrong. I did really well with y equals 1. And finally, the last one is the function. Y equals e to the x. So if I plug that in, what do I get? I get x squared times e to the x, so x cubed, because ln of e to the x is x. So I get that. I take the derivative. And does that have a solution? No. In some ways, it's not obvious that it doesn't have a solution, because this is actually a type of thing that we can't actually easily algebraically solve. But the first term, 3x squared, is non-negative because it's a square, and for e to the x is always positive because e to the x is always more than 0. So the whole thing is always more than 0. So all this work, all we did was we found that the only possibilities were corners. And so now, as with the other one, we plug those in. So if I put in f of 0, 1, I get 0 plus 4. If I put in 4, 1, I get 4. In some ways, as I knew it would, because we here show that when y was 1, f is just the constant 4. So whatever I plug in for x, I'm going to get 4. And if I put in 4e to the 4, I get 16 plus e to the 4. Oh, I lost a 4. And so this is local min, not local, global min. And this is x. Right, so now I missed the 4 at first, so put it at the end. In some ways, it wasn't a big deal because I just noticed it's definitely bigger there. Oh, 64. Oh yeah, 64. Thank you. I messed up both of them. So I did that very well. Sorry about that. But it ended up being a fairly simple one because there were no critical points in the function when I plugged in the boundaries. There were no critical points that we cared about. So the only thing that mattered were the 3 corner points. So any questions on this? So 8. So it says here's a function, and we're going to use the disk of radius 2, which means we're doing x squared plus y squared is less than or equal to 4. Okay, so again, we get the critical values. And this in some ways for this part is fairly nice because our two partials are just in terms of one variable at a time. So for example, first one simplifies, I can pull out 3x, and so I get x is equal to 0 or 2. The second one I can pull out 4y. And I get that. So since I did so well in the last one, let me wait a minute. Don't tell me if I messed up. Okay. So this gives us a bunch of points, some of which we might not care about. So we have either x is 0 or 2 and y is equal to 2. So let me just start listing them. We have 0, 0. We have 0, negative square root of 2. We have 0, positive square root of 2. And we have 2, 0. We have 2, negative square root of 2. 2, positive square root of 2. And now the question is, are any of these points ones we don't care about? That we're checking. Are they in the region that we're looking at? So any of these ones we don't care about? Yeah, the last two. So these two are outside the circle, so we don't care about those two. All the other ones are inside the circle, either on the circle or inside the circle, so they're okay. So now we have to look at the boundary, and this is similar to what we did before. So the boundary is x squared plus y squared is equal to 4. Looking at this, which one is going to be easier to solve for? Do we want to solve for x or y? Right, because if I solve for y, I can do y squared is equal to 4 minus x squared. And since both the terms with y in it are even powers, we're not going to have to worry about square roots. That second term is the x cubed. So plug in that into the original function. And now I'm deciding if I want to square it. Yeah, take the derivative first. Maybe, yeah, why not? So then we check that. Get that lovely thing. No, because right, we have y squared. So y to the fourth is y squared squared. I could have, of course, solved for y, in which case it would have been the square root. And then, again, I just get it squared. So, as I said, kind of lovely thing. So I have an x cubed. I'm assuming I'm making I'm doing a silly thing here, but oh, actually, I think I remember. So this is equal to x 4x squared squared. Give me a second. My battery's dying. I have to plug in, so sorry about that. And that doesn't factor nicely. So obviously one is x equals 0, but let's see, do we have that if x is 0, then y is plus or minus 2. So we do get those points. Oh, lovely. So x is equal to 0, which gives us the points 0, 2, and 0, negative 2, of which we already had. No, we didn't have either one. And then the other one you said is so it's this 3 plus or minus plus. Oh, okay. So actually, I should be able to do this in my head, right? So negative b, so right, okay, so I get these two other points. And now, are those both inside the circle? Oh, no, different ones? Yes, okay. So, in some ways, since it's getting messy, I have these points, I have these points, and then I have these other 2 points, which is 6 plus or minus 9 plus, yeah, so 6 plus or minus square root of 41 over 8, whatever those numbers are. And then whatever you get when you plug that into that. So Jiang is right. We have the negative 0.43, 1.95, and negative 0.43, 1.95. Wait, is there only one? Oh, 2 of them. I see. So we get 4 other points. Because x is going to, there are going to be 2 possible x's. And then you would plug, so these 4 points. This is only one new one, but these points from up here, these points here, plug them all into the function. And whichever one is biggest is the absolute maximum, which if you don't mind, I can let me check. I might actually have its solutions open. Let's see if I do. Nope. But Yang, if you want me to give you number answers at the end of class, remind me and I'll open up the solution manual and let you know what works. But any questions on the steps? The steps themselves aren't too bad, although the arithmetic is, and a bit of the algebra is a mess. What do you mean? So in which part of problem 2? Right, so what would have happened is, so that would have meant that you would have solved for x in terms of y, sort of like we did here. No, here we solve for y. But if we solve for x in terms of y, then those would have been the boundaries. And when we plug those in, you'll see that those both give the function a 0, which didn't come into the problem. And that will always work out. So we have something like that, it's always going to work out. That doesn't matter which way you do it, or better be true. Was it? I forget. No, because the function was, if we're looking at number 2, the function in 2 was xy. So 2, 0, negative 2, 0 gave 0. Just like, so the maximum was at root 2, as Shing says. So we use the endpoints 2, 0, negative 2, 0, which when we plugged into the function gave 0. 0, 2, and 0, negative 2, when we plug into the function also gives 0. Okay. Okay, well, let's do another one, except with solving it in a slightly different way so that we can move on with it. So this officially is 2.11, but you'll see the problems are similar. Sorry about that. 2.11. We didn't really talk about this, but oh, that's right. So talk to me at the end of class, Jane. Sorry. So Lagrange multipliers are using the idea that if we have a function subject to another function, and officially we need to write that in this form, a function that we're setting equal to 0. That's never really going to matter because once we take the derivative constant will be 0 anyway, but officially we have the setup where we have a function and it's subject to a function that we're setting equal to 0. And what I said quickly yesterday was the solution will happen when the gradient of f and the gradient of g are parallel. So as usual, we get the gradients. Deciding if I want to leave it. Change my problem. Oh, that's okay. Yeah, that's fine. So I changed the problem from what I originally had, but it still should work. We'll see. So we take the two gradients, and what the theorem says is at a maximum, one is going to be a scalar multiple of the other one. So the two gradients are going to be parallel, and so therefore there will be a lambda, which is called the Lagrange multiplier, so that these are equal. So I take gradients, and set them equal. Max. So at global maximum, we'll get this. And also global minimum. So you can see what we have is we have two equations, and we also still have the constraint. So we have three equations with three unknowns. And I messed up, so we'll see if it still works, but go into it. So what I can do is do a substitution, so solve for one of the variables in terms of the other two. So I can get my original one was definitely nicer. So I might start this and it might end up being one we don't really want to solve, but sorry about that. Oops, I don't want to do that. That'll be really bad. Really bad day. Sorry about that. Today might be a short class. I'm not solving things real well. once I get x and y, I can plug it in here, and we'll find out in a second if we can actually solve it. So I get a common denominator, I'm going to multiply through, and luckily this isn't on the test, so if you don't mind. Sorry about that. Let me start again. Sorry about that. Let me do one we can actually solve. Wow, did I do that well? One. So this one works out a bit nicer. So this one is pretty easy. What's the only way this is true? So either x is equal to 1 or lambda is equal to, oh, oops, x equals 0 or lambda equals 1. Okay. So let's do lambda equals 1 first. So lambda is equal to 1. Then what does it give me for right? Because it gives me 4y minus 4 is equal to 2y, and 4y is equal to 2. And then this gives x is equal to plus or minus the square root of 5. Oh, so I plugged. Oh, I don't know where I get it from. That should be a 3. Wait. Yeah. So I plugged in y equals 2 into here. So I get x squared plus 4 is equal to 9. Okay. So the other possibility is x equals 0, which doesn't do anything. And sorry, I'm being messy again. Doesn't do anything for the first one, but for the x squared plus y squared, what does it give me for y? Right, so plus or minus y equals plus or minus 3. And therefore it gives us the point 0, -3, and 0, 3. Notice we haven't actually then solved for lambda, but we don't care what lambda is. Lambda is just something that's going to give it something. So if y was 3, we could solve for what lambda would have to be for that to work, but it doesn't really matter because we do need to make both equations 0. And then from here, it's now like the other one. So what Lagrange multiplier does is gives you solutions on boundaries. So if this was like the other problem we did, x squared plus y squared is less than or equal to 9, we still have to do the first step where we find possible critical points and then get the boundaries using this. So this is what we do instead of solving for x or y in this equation and plug into the other one and then taking the derivative to find critical points. And then once we do, as I said, it's the same, plug them all in. These are all the possible possibilities. And the biggest is the global maximum and the smallest is the global minimum. So it's really just a second way of solving for possible points on the boundary, which is why I don't mind taking it off the test, because you could have always have done this with the method we used before. So the idea is, again, so here's a quick idea, which is, suppose I have, here is a graph Yes, so we only need the second derivatives if we want to find a local minimum or maximum, because we know, just like in Calc 1, if we want to find the absolute maximum, we know absolute maximum and absolute minimums either occur at critical points or at the boundary. And so once we get the critical points, we don't care, we don't have to check if it's a local minimum or local maximum, because that'll take care of itself once I plug into the function. Whereas if I'm looking for the local minimum, local maximum, I do have to plug it in to see which one it is. So for this one, we don't have to look at the determinant. So let me go back. So here's our, just drawing a random curve. This is our constraint. And now what I'm going to do is graph level curves. So suppose this is a level curve for f at a particular value, and this at another value, and then I just keep going. And suppose these are increasing values. then the maximum is there. And what we're looking at is if I look at the tangent line to the constraint at that point and look at the tangent line to the level curve at that point, you can kind of see, and this is just the intuition, you can see that those tangent lines are going to be parallel. Unless you try drawing corners, and we don't want any functions at, sorry, where the derivatives aren't nice, the two tangent lines at that point are going to be the same. And that's saying that the gradients must be parallel. So in some ways, it's this kind of intuition where we're graphing the two. And same thing, if I kept going and wanted to find a minimum, again, where the level curve hits the function, again, they'd have to be parallel, as long as we don't allow corners. All right, so since this isn't on the test, and since it is just kind of its second way of finding it, let me do the usual thing, which is we now have 15, 20 minutes or so. Let me get into chapter 3, which we did really, really quickly yesterday. Talk about it a little bit. And then, you know that's not on the test, stop. And then, as I said, what I might do tomorrow is just one more example to show what's going on. So kind of the abbreviated intro into chapter 3. Yeah, so tomorrow I might do one example at the beginning doing integrals to keep you in practice because Monday's a holiday. But other than that, it's just going over the questions on the review. And you'll have the answers for the review later today, somewhere around 4 or 5, which I'll put on Blackboard. So with the quick intro, I'm not going to talk about too much about the definition of multiple integrals, but show how they work. And you'll see that that part of it, at least part of it, is similar to the Calc 1 with the partial derivative piece. And I think we already did one. Which is, this is kind of the equivalent to a partial derivative going the other way. So an antiderivative, which is, here we're taking the antiderivative of this function with respect to x. And the idea is just like with partial derivatives, which is we're taking the antiderivative with respect to x, so we assume y is a constant. And so therefore, what is the antiderivative of that first term? I'm actually getting ahead of me. So the y is a constant, so it just stays there. Antiderivative of 3x squared is x cubed. So we get that. Y is a constant. Antiderivative of constant is the constant times x. So I get that. And then, as usual, we get a plus c, but it could be any function that only has y's. Because we know if we want to go backwards, I can take the derivative of this, and I should get back what I start with. And I know the derivative of any function that just has y's in it with respect to x would be 0. So instead of just a constant, it can be a constant in terms of y. It's the same thing. In terms of y. except it can be things where you have to use at least a simple substitution. What's the antiderivative of e to the xy with respect to y? Right. Because it would be just as if it was e to the 2y. The antiderivative of e to the 2y is e to the 2y divided by 2. Because you do the little substitution, you let u equals 2y. Derivative is 2, you don't have it, so you divide through by it. Here we have e to the xy, you let u equals xy. Its derivative with respect to y is x. We don't have it, so we divide through by it. And then, of course, the second term is like the last one, just constant times y. And now our constant might have x. And of course, there can be, let me make it a simple one, definite integrals. And as with one variable ones, it's again the two-step process, which is you take the antiderivative and plug in the endpoints. So take the antiderivative with respect to x. The only thing you have to remember is here we're plugging in 4x because we're doing the integral with respect to x. So when I plug in 1, I get y. And when I plug in 0, I get 0. So at the end of it, I get back a function just in terms of y. So if I have a function of x and y and take the antiderivative with respect to x, I get back a function just with y. So single integrals like this are pretty much just the backwards of antiderivatives, similar to, and I won't actually do this now, but suppose I made this this. Just like single integrals, they can get more complicated. What method will I have to use to do this integral? Right, so this would have to be integration by parts because I have a product of two pieces that both have the variable I care about, x. So this would be by parts. So just like with one variable, there can be substitution, there can be integration by parts. Since we're doing this quickly, I'm not going to do that today. But any questions on the idea? Because that's all it mostly is. So let me put it together, kind of the full thing. And kind of the full thing is we're having a double integral. And also, once we have double integrals, we can have the limits being functions. Although there's a bit of a caveat there, which I'll talk about after we do the integral. So this is a full double integral, and there's no reason we would stop at 2 variables. We can have 3 variables or 20 variables or however many we want. And the way it works is we have an integral inside of an integral, and we work our way out. So we leave the outside integral alone. We take the antiderivative, so again, the two-step process. Take the antiderivative of our function with respect to y. The antiderivative of that with respect to y is xy cubed. Again, for our limits, we remember that we're plugging that in for y. So put in y equals x, which gives me x times x cubed. Plug in y equals x squared, which gives me x times x squared cubed. Which gives me this. And so now putting it together, you can see what happens is after I do the inside integral, I'm getting rid of one of the variables, and I get back an integral that just has one variable left, so a more basic integral. And I get back whatever the number is. And unlike the last ones, where it's just antiderivative, this actually gives us something. So if you remember from Calc 1, what the single integral gives us is the area, and there's going to be a little bit at the end, the area under the curve over the interval we're looking at. So what do you think this 3/40 represents? Right. So this is we have some three-dimensional region, and we're integrating over this space. So we just care about the height above this region. And we're going to get a volume below that curve in that region. And the reason I said mostly is just like with single integrals, when I said that the single integral gives us the area under the curve, is that completely right? And let me make my question a bit more specific. If I do this, right. If I do this, what this integral gives us is the area above the x-axis minus the area below the x-axis. So it's going to be similar. It's going to give us the volume above the xy plane minus the volume below the xy plane. Here that doesn't come up because the function is more than or equal to 0 ever on the region, but in other cases it might. Also, here I did it dy dx, but now that I've drawn the region, I can also do this the other way. So I still have the function. And now with it, let me talk about how we set up. And this might be about as far as we go. So given this region, what I'm looking for the limits is I'm looking for the inside variables, I'm looking for the smallest function to the smaller function to the bigger function. And then on the outside, I'm looking for what values of that variable is that true. So looking up here, actually, I think I will do one more because it'll make it a bit more obvious. If I'm looking at this, then if I draw a typical line, the bottom curve is x squared, top curve is x. So those are the limits for y. And that is true over the whole region, which is from x equals 0 to x equals 1. If I do dy, I'm assuming y is a constant. So now I'm drawing this way. And now what is the smaller function? Right, it's the one on the left. So it's x equals y, to the one on the right, which is y equals x squared, which is x equals square root of y. And that, again, is true from y from 0 to 1. So we can do it either way, either dx dy or dy dx. So let me do the two setups. Because I'm just going to worry about the setup, let me make it a fairly easy function. So what I'm going to do is I want to integrate this function, which is going to give me the bump under that curve above this region down here. And so obviously, this being the quick intro, I'm not assuming you completely understand it after this. Obviously, after the test, we'll have to do this a bunch more. So what we're going to do is set it up both ways and see what we get. Let me actually draw the picture again without my shading. So what we're looking for, if we do dy dx, I'm saying if I draw a typical x equals constant, I want what is the bottom function to what is the top function. So here, what is the bottom function? 0. And what is the top function? Right. And the idea is it depends. So what I have to do is say, well, at this point, which is the point 1/2, 1/2, so 0 to 1/2, the bottom function is 0, and as you said, the top function is x. But then from 1/2 to 1, now the top function is instead 1 minus x. So for dy dx, what we're looking for, what is the bottom function to what is the top function? And then the outside limits will say what values of x is that true. So let's do the same thing for dx dy. Now we're saying let's let y be the typical constant and ask the same type of question. What's a smaller to what's the larger function, which means left. So what is the function that's on the left? Y equals x, so x equals y. And what is the function it hits on the right? X plus y equals 1. So x equals 1 minus y. And for what values of y is that true? 0 to not 1, but just the 1/2. And so these two sets will give us the same thing. So this is what where we're going. And over the next few weeks, we'll do this, then we'll do it with a variation called polar coordinates, and then we'll do triple integrals. And with triple integrals, we'll have cylindrical coordinates and spherical coordinates for special cases. We'll do a couple applications, and then we'll go into chapter 4, the last thing, which is more complicated applications of multiple integrals. So pretty much we're going to be doing multiple integrals for the rest of the course, but it's not on test 1. So let me stop there. So as usual, I'll stop recording, and then you'll let me know if you have questions.